circular waveguide. So now using this Hz, we need to find out what are the field components that are propagating through the circular waveguide. So now let us apply the boundary conditions and find the various field components. So when we are applying the boundary conditions, that means along the surface of the circular waveguide at rho is equal to a, that means we have taken a is the radius of the circular cross section and rho is at any particular point. Suppose at rho is equal to a, that means along the surface of the circular waveguide, we get the field component E phi to be 0. Okay, that means how we define it as dou Hz by dou rho at rho is equal to a is 0. Okay, so we take this condition and we find out what are the eigenvalues for our characteristic equation. So dou Hz by dou rho means our Hz is equal to C naught Jn of rho h cos n phi e power minus gamma z, and so we want dou Hz by dou rho, that means we have to differentiate this Hz with respect to rho. When we differentiate this with respect to rho, here C naught is constant, cos n phi, as we are differentiating with respect to rho, cos n phi remains constant and e power minus gamma z also remains to be constant. There is only the differentiation exists for one term, that is the Bessel's function Jn of rho h. Okay, so this while we get the differentiation for this, then the differentiation for Bessel's function we get, and so we can represent it as Jn dash. So that can be represent it as Jn dash of rho h, but at rho is equal to a, simply we can write rho is equal to a and Jn dash rho ah, Jn dash of ah is equal to 0, because the differentiation of this to be equal to 0 and all these are remains to be constant, obviously only the differentiation of the Bessel's function has to become 0. So for this Bessel's function equation, so we have different roots, there are n roots will exist because this is a nth order Bessel's function. So let us represent the nth root of this, the Jn dash ah is represented by Pnm, that means there are n roots, of that m root we are going to find, and so we call it as Pnm dash is equal to ah. So from this we can find what is h. So h is equal to Pnm dash by a. Okay, so we can substitute this in the Hz also. So simply we can write Hz is now equal to C naught Jn of rho is a, okay, and h is, okay, we take it as rho, h is Pnm dash by a cos n phi e power minus gamma z. So h is equal to, due to this h we get the Hz, and Hz is represented in this form. So now by using this Hz we can find various field components, and so those field components, that means already we have seen there are different field components exist. See, if we take this T wave equation, already we get Ez is equal to 0 and we got Hz. Okay, so we need to find the remaining field components, that is E rho, E phi. Similarly, we need to find H rho and H5. These field components need to be obtained. So, now let us define the field component first E rho, where E rho is equal to minus j omega mu by h square 1 by rho dou hz by dou phi. So, we want to obtain the differentiation with respect to phi. So, what is hz? We write hz is equal to C naught Jn of rho h cos n phi e power minus gamma z. So, we want the differentiation of this hz with respect to phi. As we are going to differentiate with respect to phi, then all the rho terms will get constant. That means all these terms will get constant, and simply differentiation of this cos will become minus sine. So, here is a minus and this minus becomes plus. So, we get j omega mu by h square 1 by rho C naught Jn rho phi plus sin Jn rho phi into sin n phi e power minus gamma z. Okay. So, now we have a lot of coefficients, constants here at the beginning. Simply we can all write this as some arbitrary constant with respect to rho as C naught rho, and can substitute, can write it as C naught rho, Jn of rho we write as it is, h we substitute Pnm dash by a sin n phi e power minus gamma z, where C naught rho is equal to j omega mu by h square into 1 by rho C naught. So, that term we have taken it as a constant, arbitrary constant. So, we obtain the one of the field component E rho. Then we need to find out E phi, H rho and H phi. So, let us define how we get E phi. E phi we can obtain it as j omega mu by h square dou hz by dou rho. E phi, E rho we got it as minus j omega mu by h square 1 by rho dou hz by dou phi. Now, we want the differentiation of hz with respect to rho. So, let us write hz here. Hz is equal to C naught Jn of rho h cos n phi e power minus gamma z. Okay. While differentiating hz with respect to rho, that means the differentiation of this term will exist and all the remaining remains to be constant. So, we get C naught as it is, cos n phi e power minus gamma z as it is, and the differentiation of this Jn rho h can be represented it as Jn dash rho h, where rho is equal to a. Okay. So, we can also write it as Jn dash ah, and h is simply Pnm dash by a we can write. So, by substituting that here we get, okay, Jn dash rho Pnm dash by a cos n phi e power minus gamma z, and this entire constant we can take it as C naught j omega mu by h square as C naught phi. So, initial arbitrary constant we take it as C naught phi Jn dash rho Pnm dash by a cos n phi e power minus gamma z. Similarly, we also obtain the field expression for h rho, because we already know Ez is equal to 0. So, we find h rho. H rho can be obtained as minus gamma by h square dou hz by dou rho. So, dou hz by dou rho means here we are obtaining this, and now we can define a parameter, that is wave impedance. So, using this wave impedance we define, simply wave impedance can be obtained as it as E rho by h phi or minus E phi by h rho. So, whereas as we want to find out H rho, we can find out this H rho by taking this as minus E phi by ZZ. Okay. So, this is E phi, this is E phi, and minus E phi by ZZ means minus C naught phi by ZZ. So, this is nothing but representing the wave impedance, and so we get the remaining entire equation. Simply we can obtain H rho is equal to minus E phi by ZZ. Similarly, we can also obtain H phi using this relation. H phi is equal to E rho by ZZ. So, already we have obtained E rho, and so we can obtain H phi also, and H rho is equal to simply minus E phi by ZZ. So, this is my E phi by ZZ. So, the same equation we get here also, and so H phi also can be obtained as E rho by ZZ. So, we have already calculated E rho. So, C naught rho by ZZ, Jn rho Pnm dash by A sin n phi e power minus gamma z. Okay. So, now let us derive the cutoff wavelength from this TE wave equation and TE wave field expressions we have derived. So, for this cutoff wavelength, we start from our characteristic equation, that is gamma square plus omega square mu epsilon is equal to h square. So, or we can also take that as gamma is equal to alpha plus beta j beta. For the wave to be propagated through the waveguide, it should be having no attenuation, that means alpha should be equal to 0. Okay. So, when alpha should be equal to 0, that means root component should be less, okay, less than 0. So, anyhow, let us take that condition. So, we know that at the cutoff frequency there is no mode propagation vanish, and so that means alpha is equal to 0. So, at this cutoff frequency, that means actually we get gamma is equal to root omega square mu epsilon minus omega c square mu epsilon. So, at cutoff frequency omega also becomes omega c, and so root also will vanish. So, this gamma will be equal to 0 for the mode propagation. So, let us take the same condition, that the gamma is equal to 0 for mode propagation. So, when gamma is equal to 0, that means alpha plus j beta is equal to 0. Okay. Anyhow, we have defined the beta, that is beta is equal to root omega square mu epsilon minus n pi by b whole square plus m pi by a whole square, and this is nothing but actually if you take for the rectangular waveguide we have considered this is the beta, and here this n pi by b whole square plus m pi by a whole square is nothing but omega c square mu epsilon is nothing but this is the term omega c square mu epsilon, or simply we can also take it as h, because we got for a rectangular waveguide only I am considering h square is equal to a square plus b square. Okay. So, h is nothing but this is m pi by a whole square plus n pi by b whole square. So, this term we can consider it as either h square, or we can also consider this term as equal to omega c square mu epsilon. So, let us represent both the relations, that is beta is equal to root omega square mu epsilon minus h square, or we also call it as root omega square mu epsilon minus omega c square mu epsilon, because this term is equal to omega c square mu epsilon, also this term is equal to h square. So, that means now we have the relation that this is nothing but h square is nothing but equal to omega c square mu epsilon. We also have this relation. Anyhow, where h is nothing but Pnm dash by A for TE mode propagation. Anyhow, we have not discussed for the TM mode, but similarly we can say for TM mode of propagation h is equal to Pnm by A. Okay. So, there is a slight difference between TE and TM waves. That wave equation remains to be same, but here we have Pnm dash by A is the eigenvalue, and here Pnm by A is the eigenvalue for TM mode. Let us take the relation that h square is equal to omega c square mu epsilon and find out what is cutoff frequency from this. Then we can find out the cutoff wavelength. Okay. So, in this h is equal to omega c root mu epsilon, but we know that c is equal to 1 by root mu epsilon, where c is the velocity of light. So, root mu epsilon we can write it as equal to 1 by c, omega c we can write it as 2 pi fc. So, here we got the relation fc by c, but we know that c by fc is nothing but equal to lambda c. So, fc by c we can write it as 1 by lambda c. So, finally, we get the relation between the h and the cutoff wavelength. So, we can say using this the cutoff wavelength lambda c is equal to 2 pi by h, where h is equal to Pnm dash by A for TE mode and which is equal to Pnm by A for TM mode. So, the cutoff wavelength for TE and the cutoff wavelength for TM. Okay. So, once we get the cutoff wavelengths, we can define what is a dominant mode and what are the degenerate modes. Okay. So, now let us see what is a dominant mode from this relation lambda c. So, dominant mode means we say that the mode which is having the higher cutoff frequency, that is propagating through the waveguide, we call it as a dominant mode. So, here let us define the dominant mode first. So, coming to the dominant mode which is having the higher cutoff frequency, that means we want higher cutoff wavelength. Okay. We want lambda c relation, that is we make use of the same relation. For example, if we take the TE mode, lambda c is equal to 2 pi A by Pnm dash. So, dominant mode means the mode which is having the higher cutoff wavelength, lambda c should be maximum. So, for getting the maximum lambda c, we require the denominator to be small, that is Pnm dash should be small. So, we need to have the what are the values of the what are the eigenvalues for different values of n, m. So, now let us simplify this for obtaining this Pnm dash. Then we have a set of table with representing the roots for Pnm dash for different values of n and m. Okay. So, these are for n and these are for m. So, for n 0, 1, 2 and for m 1, 2, 3 we have different values, and in this entire table we identify this value to be minimum. So, the Pnm dash roots are minimum at n is equal to 1 and m is equal to 1. So, at this minimum value we get the maximum cutoff wavelength. So, the mode, this is Pnm dash means we are considering this for the TE mode. For TE mode, for n is 0 and m is 1, okay, we consider it as the dominant mode. Sorry, n is 1 and m is 1, okay, this is n is 1 and m is 1. So, for TE mode, we consider n is 1 and m is 1 as the dominant mode, that means TE m n means m is 1 and 1 1. So, this is the dominant mode in the circular waveguide. Okay. So, for Pnm dash is equal to 1.841 we get the minimum value for N1 and M1, and hence TE11 is the dominant mode. For TM mode, if we consider, we need to take the eigenvalues for PNM. We need to take the eigenvalues for PNM. We need to find the roots for PNM. So, if we find the roots for PNM for different values of N and M, here we can find this is the least value. That means N is 0 and M is 1. So, if we consider for TM mode propagation, for TM we get for minimum value for N0 M1, and so the dominant mode is TM Mn, that is 10. TM10 is the dominant mode. So, we just once see for the rectangular waveguide also here. So, for rectangular waveguide, in TE10 is the dominant mode and TM11 is the dominant mode. But for in circular waveguide, TE11 is the dominant mode and TM10 is the dominant mode. So, while there is a transition from rectangular to circular, the dominant mode changes from TE10 to TE11 and TM11 changes to TM10. Okay, this is one important thing to be note here. And so, now we define the degenerate mode. So, the modes which are having same cutoff wavelength, we call them as the degenerate modes. And if you observe in the previous table here, if you see this case, here we have 3.832, that means N is 1 and M is 1 for TM, and here also we have the same 3.832 for TE mode N0 M1. So, for TE N0 M1 and for TM M1 N1 is having the same value 3.832. See, for TE10 we have 3.832, for TM11 we have the same 3.832. So, we have P01 dash is equal to 3.832 and P11 also is having 3.832. So, for these modes, because as lambda C is equal to 2 pi by Pnm dash for TE, this is equal to 2 pi by Pnm for Tm. This is for Tm and this is for TE. Both values are same, Pnm dash and Pnm are same for TE 01 and TM 11. So, these two modes are having the same cutoff wavelength and hence these modes we call them as the dominant degenerate modes in the circular waveguides. And similarly, dominant mode is TM10 or TE11 is the dominant mode in the circular waveguides. So, let us see the summary. In this session, we have discussed about the circular waveguides and what is the mode, TE mode, that is propagating TE wave equation and the field expressions in the circular waveguides. And also we have discussed the cutoff wavelength, we have derived the cutoff wavelength, and from the cutoff wavelength we have find out what is the dominant mode and what are the degenerate modes in the circular waveguides. Okay, thank you.